Hey there, buddy and statisticians. It's Miss Perry, and I'm really excited to walk you through how to calculate confidence intervals. But first, we need to take a step back and talk a little bit more about margin of error. So originally, we said informally, margin of error was our wiggle room around our point estimate. So whatever value we were estimating for that parameter, we would have a margin of error that allowed us to go up or down a set amount to kind of create a larger interval to capture that value. Well, our margin of error is specifically calculated in the following way. It's something called a critical value times the standard deviation of the statistic. Now, we're pretty good on standard deviation. Let's talk more about critical value. So the critical value gives us some portion of our standard deviation that we need, and it has some special notation. It's z with an asterisk. Now, when we've been talking the last couple of days about 95% confidence intervals, we said that our margin of error would be about 2 standard deviations. So in that case, the critical value would be 2. Let's calculate some critical values so this makes a little more sense to you. So here's an example. Calculate the critical value for a 95% confidence interval. Now, we've already said it's about 2, but about isn't good enough. We're going to actually get a very specific value for this. So here's my normal distribution. We know from the empirical rule that about 2 standard deviations above or below the mean gets me 95% of my data. Well, if that's the case, then that means that there's 5% data left over for the 2 tails. Well, there's 2 tails, so I'm going to divide that by 2. That means there's 2.5% of all possible values are in each tail. As an area, that looks like 0.025 on either side. I need to find at what z-score do I have 0.025 area up to. So if you know how to use your z-tables, you can go there, and you're not going to look this up as a z-score. Remember, that 0.025 is an area, so you're going to look in the body of the table for the value 0.0250 and find the z-score that's as close to it as possible. Some of you guys are more tech savvy, so let's talk about how to do this on the calculator. Under that distribution menu where we've been finding normal CDF, binomial CDF, geometric CDF, you'll find a function called INV norm. That's inverse normal. And that allows you to enter a specific area, a mean and standard deviation, and it'll return the z-score associated with it. So the area I'm looking for, 0.025, and I'm working with the standard normal distribution, so I have a mean of 0 and a standard deviation of 1. This in the calculator returns negative 1.96. Now, if you're looking this up in the table, you should have gotten the same answer. Because of the symmetry of my bell curve, I know my negative z-score is negative 1.96, and my positive z-score will be positive 1.96. So my critical value, z asterisk, is going to be plus or minus 1.96. And as we expect from our empirical rule, it's about 2. Let's do another one. Calculate the critical value for a 96% confidence interval. So, if I want 96% of my data centered at the mean, again, I know I'm going to be about 2 because that's 95%. But let's look at 96. So if 96% of my data centered at the mean, that leaves me with only 4% left over for my tails. Don't forget you have 2 tails. 4 divided by 2 is 2. So I only have 2% data in each tail. So down here, this area is only 0.02. And this area over here is only 0.02. So if you're going to use the z-table, remember to look in the body of this table. This is not a z-score. This is an area. On the calculator, you would use inverse norm, enter your area, comma the mean and standard deviation of the standard normal, and it'll return negative 2.05. Because of the symmetry of the bell curve, my negative z-score and my positive z-score will be 2.05. So z asterisk, my critical value, is plus or minus 2.05. Let's put critical values to work and calculate some confidence intervals. Here's our first example. From a large jar of pennies, students took a simple random sample of 102 pennies and found 57 of the pennies in the sample were more than 10 years old. Part A, calculate and interpret a 99% confidence interval for the true proportion of pennies in the jar that are more than 10 years old. So, first thing I need to know is what statistic am I looking at? What parameter am I trying to estimate? Well, it tells me that I want a confidence interval for the true proportion. So I'm looking for a p-value. That means I'm going to be working with p hat as my statistic. I'm going to try to estimate a p hat. So in general, when I'm finding confidence intervals, remember it's my estimate, so p hat, plus or minus my margin of error. But now we know that margin of error is a critical value times the standard deviation. So p hat plus or minus z asterisk times sigma sub p hat. Lots of notation here. Hope you guys are being able to keep up. Let's calculate each of these three pieces one by one. Let's start with the p hat. P hat is my sample proportion. In my sample, I had 102 pennies, and 57 of them were more than 10 years old. So 57 out of 100 gets me a p hat value of 0.5588. That's my sample proportion. So according to this sample, I'm thinking that 55.9% of all the pennies in this jar are going to be more than 10 years old. And we're going to calculate an interval around that we hope captures the true proportion. What else do I need? I also need my standard deviation for my sample. So remember back from the last unit that sigma sub p hat was the square root of p times 1 minus p all over n, my sample size. Now I know we don't know the true proportion, and that's what Chapter 8 is all about. Because we don't know the true proportion, it is okay for us to use our p hat in place of p. So this is going to be the square root of my sample proportion, 0.5588, times 1 minus p, 0.4412, divided by my sample size of 102 pennies. That comes out to 0.04916. So that's the standard deviation of my sample proportion. The last thing I need is a critical value. So remember, if you are unsure how to calculate critical values, go back over the last couple of examples. But if I want a 99% confidence interval, that means that I'll only have 1% in my tail. I got two tails, so when I do my inverse normal function on the calculator, I'm not going to put in 1%, I'm going to put in 0.5%. That'll spit out for me critical values of plus or minus 2.58. Let's put together our interval. So my interval is my p hat 0.5588 plus or minus my critical value 2.58 times my standard deviation. Simplify by multiplying my critical value times my standard deviation to get my margin of error, And if I'm more comfortable using interval notation, I'll see that this is the interval from 0.4320 to 0.6856. So we're thinking that the real true proportion of pennies in this jar that are more than 10 years old is going to be between 43.2% and 68.6%. So let's interpret our confidence interval. So we are 99% confident that the interval from 0.4320 to 0.6856 captures the true proportion of pennies in the jar that are more than 10 years old. I hope this is making sense and that you're not having trouble following along. Let's look at a part B for this question. So here's our same jar of pennies. We took our same simple random sample, all the same information from before. Part B, is it plausible that exactly 60% of all the pennies in the jar are more than 10 years old? Well, here's our interval we just calculated, and we're asking, is 60% a possible value or a plausible value for the true proportion? Well, 60% equals 0.6. Is 0.6 in our proportion? Sure. So yes. Since 0.6 is contained in the interval, it is a plausible value. Let's do one more fun example before you're set out on your own. According to an article in the San Gabriel Valley Tribune, most people are kissing the right way. That is, according to the study, the majority of couples tilt their heads to the right when kissing. In the study, a researcher observed a random sample of 124 kissing couples in various public places and found that 83 out of 124, or 66.9%, of the couples tilted to the right. Construct and interpret a 95% confidence interval for the proportion of all couples who tilt their heads to the right when kissing. All right, so we're looking again for a proportion. We'll construct confidence intervals for means later in the week. So we're going to have the same setup. We're going to have p hat plus or minus a critical value times sigma sub p hat. Our statistic plus or minus the critical value times the standard deviation of the statistic. First things first, p hat. It's actually given to us. Remember, the researchers found that 83 out of 124, or 66.9% of couples, were tilted their heads to the right when they were kissing. So p hat equals 0.669. Let's get our standard deviation. Sigma sub p hat will be the square root. Remember, in this case, it's okay to use p as our value because we don't know the true proportion, so we're going to substitute in our p hat. 0.669 times 1 minus that, 0.331, divided by our sample size, 124 couples. This gives us a value 0.0423. So statistic, standard deviation, and now I need a critical value. So I'm looking for a 95% confidence interval. Luckily, we've already calculated the critical values for 95% confidence intervals. It was the first example we did. So if you're unsure about how to calculate it, go back and check that part of the video out. But it told us that the critical value was plus or minus 1.96. Let's put it all together into an interval. P hat plus or minus the critical value times the standard deviation.